everyone and good day. So we from Group 10 will be presenting about the hip implant design. So Group 10 consists of 5 group members. The first one is KEAT, NURUL SYAFIQAH, CHOONG, HAFIQ, and also me myself, ALIA AIRIN. I will be presenting about the introduction to hip implant. The first thing we need to focus on is to get to know the hip. The hip is said to be one of the largest joint in our body, so it consists of a ball and a socket joint. That is the two most important part that we need to understand here. So the socket is technically the acetabulum, which is the part of the pelvic bone, and the ball is the femoral head, which is right where the end of the upper femur. The ball and socket that we discussed earlier is actually covered with a smooth tissue that is called as the articular cartilage that serve as a cushion that enables them to move easily or smoothly. So there is also a very thin tissue that is called as synovial membrane that surrounds the hip joint. So this membrane serves as a lubricant to eliminate almost all friction during hip movement. The application of the total hip implant. So when we are talking about total, it means that the whole hip is being replaced. So we are making a hip prosthesis that replaces a hip joint for a patient that suffers from injuries or suffers from osteoarthritis. So basically, the convex femoral head is placed within the concave of the acetabulum of the pelvis. So there are actually two most common types of artificial hip prosthesis. One is the cemented one and the other one is the uncemented one. For the cemented prosthesis, it will attach to the bone with a surgical cement, while the uncemented prosthesis will attach to the bone with a porous surface. So as time goes by, the bone will grow onto this surface to attach to the prosthesis. So this is the overview of the general material used. So the first term is for the femoral head, and the second term of material is for the acetabular liner. So we have the MOP, which is the metal on polyethylene. We have the MOM, which is the metal on metal. We have the COP, the ceramic on polyethylene, and also COC, ceramic on ceramic. That is all from me. Thank you.
Hi, I'm Hongkiat, and now I'm going to discuss on the design description. First of all, there are several indications for choosing a total hip implant treatment. If you are suffering from a damaged joint due to severe osteoarthritis and experiencing unremitting pain, total hip implant can be the solution. Moreover, having fracture at femoral neck or experiencing cup arthroplasty, surgery failure, total hip implant is also suitable for you. Besides, total hip implant is also beneficial for individuals with congenital hip disease like developmental dysplasia of hip, DDH, metastatic cancer, or suffered from a hip joint instability. The main objective when designing a total hip implant is to create a hip joint with high biocompatibility, high durability, and low friction. Therefore, we have chosen ceramics on ceramics total hip implant design compares with the other material designs. There are a few excellent criteria from COC design that make it to become our selection. First and foremost, ceramic has high durability and strength to meet the hip implant mechanical requirement. It also has the excellent biocompatibility and chemical stability to be implanted into human body. Besides, COC design has the lowest rate of volumetric wear over the years and exhibit excellent lubrications to reduce frictions during the joint movement. A total hip implant consists of 4 main components with acetabular cup, liner, femoral head, and femoral stem. Ceramic on ceramic design means that both of the liner and femoral head are made of ceramics. Looking into the acetabular cup, we use cemented acetabular cup design made with ultra-high molecular weight polyethylene, or known as UHMWPE. At both liner and femoral head, we use alumina as the biomaterial. Lastly, titanium alloy, specifically Ti64, is coated with hydroxyapatite HA. It's used to make the cementless femoral stem.
Hi, my name is MOHAMAD HAFIQUIZUDDIN and I will explain about the material selection and justification for the hip implant. For the cementless femoral stem, we choose titanium alloy as the material with the hydroxyapatite as the coating. Titanium has excellent mechanical properties. Because of titanium high ultimate energy tensile strength, which is 550 megapascal and 880 megapascal respectively. It makes the material suitable for high load bearing implant. It also has a low elastic modulus to mimic the bone elastic modulus as close as possible. Titanium also has a good biocompatibility. It has high corrosion resistance. Corrosion that forms layer of titanium oxide is a stable and reactive interface that becomes coated with plasma proteins. Titanium has a low density, make it 45% lighter than steel but more stronger. Because of the corrosion that may occur, the femoral stem is coated with the hydroxyapatite. Hydroxyapatite is a bioactive material that enhances the healing response and extend the implant life. It also promotes good attachment of stem to the bone cell and surrounding tissue, decrease the implant loosening chances. Besides, hydroxyapatite also is osteoinductive. It stimulates bone growth by increasing the osteoblast activity under optimized condition. Because we choose ceramic on ceramic design, for the femoral head and liner, the chosen material is alumina. Alumina has a great biocompatibility. It is a bioinert material that do not harm the surrounding tissue and bone. Alumina also has high strength and hardness, make it suitable to withstand the high load. The strength of alumina is 500 megapascal and 9 on Mohs scale of hardness. Due to high hardness, alumina has high wear and corrosion resistance and also low friction. This leads to no generation of particles that can cause an implant failure and also tissue death. For the cemented acetabular cup, the material that we use is ultra high molecular weight polyethylene, UHMWPA. It has excellent mechanical properties. The mechanical properties of ultra high molecular weight polyethylene is highly affected by its microstructure and also crystallinity. It has high impact strength, which is mimic the cartilage function in absorbing the impact. It also has a low wear rate. It is important because it can generate less wear particle and also make the implant lifespan longer. Even though the chosen materials are the best, but the materials such as metal still undergo degradation process by the corrosion. Corrosion at the articulating surface of the implant can be classified as the tribocorrosion. It usually occurs between the interaction of acetabular component and femoral head, resulting in the generation of wear and increase the corrosion rate. Spreading corrosion is a particular concern in multi-component devices. When two components are in contact with each other, cyclic loading can cause micromotion between the mating surfaces. This oscillatory motion can cause localized deformation, material removal, and also transfer, known as fretting. An environmental characteristic including elevated temperature and electrolytic fluid medium with non-neutral pH and differences in material chemistry can increase the chances of corrosion on the material surface. In the hip implant, we can observe this phenomena at the titanium femoral stem. The titanium oxide that form in the corrosion, adding the burden to periprosthetic tissue, increase the surface wear. The degradation can cause systemic or local systemic reaction. Adverse local tissue reaction (ALTR) is one of the systemic reaction that associated by the metallic corrosion that release metal species into the body fluid. The ALTR associated with metal release have been observed in hip implants with metal-on-metal articulation initially, and later with metal-on-polyethylene articulation. The most accepted mechanism of ALTR is that cell damage generated by metal ions may trigger the secretion of cytokines, leading to the inflammatory reactions. In this inflammatory environment, some patients would develop hypersensitivity that is associated with poor outcomes.
Hi, my name is Chong Hui, and now I'm going to talk about the adverse reaction of metal debris, ARMD. ARMD is caused by metal degradation. One of the issues that stem from ARMD is metallosis, which is a blood poisoning condition that develops when there are high levels of toxic metals in the blood. It is reputed to occur when metal particles shed from metal hip implants or other joint replacement devices are released into the bloodstream and tissue surrounding the implant. Exposure to metal in the bloodstream and surrounding tissue can cause complications such as blood clot, bone dislocation, and fractures. If the symptoms are not treated, it can advance to surrounding tissue and cause bone death. Osteolysis is also an issue that arises from ARMD. Osteolysis is the process of destruction of periprosthetic bony tissue characterized by cavitation at bone implant. Osteolysis is induced by material wear debris, commonly PE, that cause the implant loosening and failure in metal-on-metal and metal-on-polyethylene implant. Next, I will talk about the process of fabrication and characterization tools. Different devices have different process of fabrication. For example, titanium, it starts with forging or investment casting, followed by rough machining, then polishing, lastly coating, which is plasma spraying. For UHMWPE, which is the ultra-high molecular weight polyethylene, molding and machining are essential for the fabrication process. The fabrication process for ceramics such as alumina includes sintering, grinding, and polishing or lapping. For the tools and instruments for material characterization, in terms of imaging, SEM, which is scanning electron microscope, and TEM, transmission electron microscope, are used. In terms of chemical content, XRD, which is X-ray diffraction, and FTIR, Fourier transform infrared spectroscopy, are used. In terms of mechanical strength, we will look into Vickers hardness, tensile strength, elastic shear, flexural modulus, Poisson's ratio, compressive strength, and density. In terms of surface properties, we will look into contact angle, goniometer, roughness, and wettability.
For the last part, me, SYAFIQAH, will explain about appropriate tools and instruments for the material device characterization. The 4 aspects that we want to see are imaging, mechanical strength, identification of chemical content, and the surface properties. For UHMWPE, ultra-high molecular weight polyethylene, alumina, and titanium alloys with hydroxyapatite coating. First, let's go through briefly on the characterization of each materials. Here we have image of UHMWPE under SEM. Its chemical content we get from FTIR, mechanical strength, and the surface properties. Because of its microstructure and crystallinity, UHMWPE have high impact strength, water and chemical resistance. Also possess similar density to living tissue, making it biocompatible to our body. Next, we also use SEM to the image of titanium alloy and hydroxyapatite coating, and using XRD, X-ray diffraction, for its chemical content. It also has great mechanical strength in general, making it suitable to be used as femoral stem, and with the hydroxyapatite, it promotes bone growth and good attachment. First material is alumina, also known as aluminium oxide. This image of alumina we get from TEM, transmission electron microscope, and they use XRD for its chemical content. There are no bodily functions that react with the alumina, hence the excellent biocompatibility. The fact that alumina is a compound of aluminium and oxygen should not be the cause for concern, because it is bioinert. First common instrument for imaging is SEM, scanning electron microscope. The SEM produces a largely magnified image by using electrons instead of light to form the image. The beam of electron is produced at the top of the microscope by an electron gun. Once the beam hits the sample, electrons and X-ray are ejected from the sample. Detectors collect and convert that into a signal that is sent to a screen to the final image. Next one is TEM, transmission electron microscope. TEM employs a high voltage electron beam in order to create an image. An electron gun at the top of the TEM emits electron. This beam then passes through the specimen, which is very thin, and the electrons either scatter or hit by the fluorescent screen at the bottom of the microscope. This image can be then studied directly within the TEM or in photograph. The main difference between SEM and TEM is that SEM creates an image by detecting reflected electrons, while TEM uses transmitted electrons that are passing through the sample to create an image. Next, to know the chemical contents of the material, we can use X-ray diffraction. X-ray diffraction analysis (XRD) is a technique used to determine the crystallographic structure of a material. XRD works by irradiating a material with incident X-ray and then measuring the intensities of the scattering angles of the X-ray that leave the material. We can also use Fourier transform infrared spectroscopy (FTIR). It is a technique used to obtain the infrared spectrum of absorption or emission of a solid, liquid, or gas. FTIR analysis measures the range of wavelength in the infrared region that is absorbed by the material. The sample's absorbance of the infrared light energy at various wavelengths is measured to determine the material's molecular composition and structure. Next, there are many methods, tests, and tools can be used to identify materials' mechanical and surface properties. These are some of the examples. Usually, Vickers harness test and tensor test is done to identify the mechanical strength of a material. The Vickers harness test measure the indentation hardness for small parts of or thin section of metal, ceramics, and composite. The larger the indent left by the indenter, the softer the tested materials. Tensile testing is a destructive test process that provides information about the tensile strength, yield strength, and the ductility of the material. It measures the force required to break a composite or plastic specimen and the extent to which the specimen elongates to the breaking point. Lastly, for the surface properties, we normally use contact angle test. Contact angle test generally conducted to investigate the surface hydrophobicity. A contact angle is formed when a drop of liquid is placed on a material surface and the drop forms a dome shape on the surface. The angle formed between the surface and the line tangent to the edge of the drop of the water is called the contact angle. The forces acting on the drop of the water from the surface area refers to the surface energy of the material. If the forces are strong, the surface has high surface energy, or the surface can be said to be very energetic. We can also observe the wettability of a material using contact angle test. Wettability is the amount to which a liquid can be spread on the surface, determined by the intermolecular forces between the surface and the liquid. In conclusion, many factors need to be taken into consideration to build a hip implant, and based on all materials characterization that we discussed, we believe that ceramic and ceramic hip implants are the best. That's all from Group 10. Thank you.